All right, last paper for today. I hope it works right now. Thank you very much for including our paper in this program, and thank you for everyone for staying until the end. This paper is joint work with Svetlana Briskalova, my PhD student Sven Lerner, and Martin Lettau. This paper fits perfectly into what the other two papers talked about before. We talk about firm fundamentals and firm characteristics. And as we've seen, we need these firm characteristics to build asset pricing models, for example, factor models. We need them to build investment strategies, for example, portfolio sorts, return prediction. And we also use them to build test assets, for example, sorting strategies. Now, everyone who has worked with firm characteristics knows there's one problem. A lot of companies don't have all these firm fundamentals observed. And the question that we are trying to answer here is, how much of a problem is this, and how should we deal with it? The fact that I'm giving a presentation indicates that it is a big problem, and the way how people often deal with it is highly problematic. So what you see in a lot of papers is that people only use the subset of companies that have everything observed, and we show that this will lead to a massive selection bias. Or very ad hoc imputation approaches are employed, like a median imputation, and we show this will also lead to imprecise and biased estimates. So what we do in this paper is we will provide key facts about missing firm characteristics. We will provide a solution, namely a new method to impute missing values, and we show the implication for asset pricing. I want to highlight that firm fundamentals are also needed when you do corporate finance or more broadly in economics, and our insights and methods also apply to that application. And more broadly speaking, how to deal with missing data is becoming a more and more important problem. Think about ESG data, international data, etc. And the methods and the insights from today's presentation can also be applied to that area. All right, let me start with the key findings. First, missing data is prevalent. So almost all firms have missing data, and it applies to small and large, young and mature, and profitable and distressed companies. Second, and that's a big elephant in the room, if we want a company to have multiple characteristics to be observed at the same time, we will end up with a very small sample. If we would only take the companies that have everything observed here, I would throw away 70% of all the companies, and that corresponds to 50% of the market cap. That is huge. And there are a lot of applications that require you to have all these characteristics. Think about cross-sectional, regressional characteristics, a lot of machine learning methods, etc. Number three, data is not missing completely at random. What it means is that companies that have observed data are systematically different from companies that have missing data. There are systematic patterns, so missingness clusters over time, it clusters in the cross-section, and we can show that missingness appears more likely for extreme realizations or for companies that have specific characteristics like small stocks. Fourth, it matters for returns, how we deal with missingness. So investment strategies will be more profitable out of sample if we include all stocks. We show that there's a selection bias. So if we only take the subset of companies that has everything observed, we will get biased estimates and we will get worse results with asset pricing metrics. And there's imputation bias if you use an ad-hoc method like a median imputation. You will get distorted estimates for risk premia, for example. So more broadly speaking, we think that this missing data has widespread applications if we want to tackle the multivariate challenge in asset pricing. We also provide a solution, namely a way how to impute missing values. Now, why is it a challenging problem in the first place? Well, first, we need a good model for characteristics. If we omit relevant information, we will have an omitted variable bias. Number two, and that's important, we need to estimate our model on the partially observed data, and it needs to hold on the missing data. But firm characteristics are not missing at random, and that is what is making it very challenging. Now we have a solution. Our method will be a cross-sectional and time series factor model. So first, we'll capture contemporaneous cross-sectional information with a latent factor model. For example, we can capture that small stocks are more likely to be value stocks. And second, a lot of characteristics are persistent. So there will be a time series model that also takes advantage of this information. And what is really important here, our model is going to work under very general endogenous missing patterns. That means missingness can depend on time, stocks, characteristics. It can also depend on the realization itself. That's really what is separating our paper from this literature here. So overall, we have a data-driven, transparent, and very simple to implement solution of how to impute missing values. And we show empirically that it works extremely well. So we get 40 to 50% better out of sample accuracy. And we also can make statements about what is a good way to deal with missing data. How should we impute it? We show you need both this contemporaneous cross-sectional information and the time series information. And we will provide a publicly available data set and code so that you can also use this data in your own research. So let me start with stylized facts. So we use standard data. This will be firm characteristics, monthly observed for around 50 years. It's a kind of data that we have seen for many papers, and you have also seen the previous papers. Here I'm using 45 characteristics. So it's a very representative data set. Now, first, I want to talk about how much missing data do we have. So here I'm showing you for different stocks. So here I show you over time how many stocks we have in our sample. That's the black line. So at the peak, we have around 8,000 stocks. If we look at how many of those stocks have, for example, investment information, you can see there's more missing at the beginning, but at the end is around 10 to 20% missing information. There are other characteristics like property or assets where we have 50% missing information for the whole sample. So there's a lot of heterogeneity, depends on the time and the characteristic. But let's come to the big elephant in the room. So what if we want to only look at companies that have all these 45 characteristics observed? I will end up with the blue line here. It's less than 30% of the sample that I'm left over with, and I would throw away 70% or 50% of the market cap if I only use the subset. It's not driven by particular characteristic. So if I allow up to 3 characteristics to be missing, which can be different for different stocks and different time periods, I would still throw away 50% of all the data. I would need to allow up to 35 characteristics to be missing out of my 45 to end up with a sample that covers around 97% of the data. Keep in mind, there are a lot of applications where we need this full vector of characteristics. I also want to talk more about when are characteristics missing. So here I have my 45 characteristics. I show you the overall missingness. So it's for most characteristics around 10 to 20% missingness. Some missingness will happen at the beginning. So that's for young companies that don't have a history. There's missingness in the middle and there's missingness at the end. The reason why I bring this up is because if there is missingness at the beginning, we cannot use prior information for imputation. So it matters what kind of missingness we have when we want to use some models to impute the data. So which stocks have actually missing observations? So here I'm showing you, let's look at the light blue line for investment, how much data is missing for small and large cap stocks. The black line is all stocks. So we have more missingness for the smallest quintile than for the largest quintile. If you look at investment, you have around 40% missing observation for the 20% smallest stocks, but only 20% missing observation for the largest quintile. The point here is there are complex interaction effects with size. And more broadly speaking, companies that have missing observations are different from companies that have observed information. And that needs to be taken into account to avoid a selection bias. What about the type of realization that is missing? If you look at the light blue line that shows you for investment, companies that are on average in the smallest investment quintile have more missing observations than companies that are on average in the medium investment quintile. And then you have again more missing values if you're in the largest investment quintile. So these U-shaped patterns are uniform. They hold for all characteristics, but sometimes more or less pronounced. What it means is more extreme realizations are more likely to be missing. And you can interpret that as an endogenous form of missingness. And that's actually very hard to deal with statistically. Now, if we want to build a model for imputation, we first need a good model for characteristics. So we need to leverage the dependency in characteristics. So first fact, characteristics are quite persistent. So what I'm showing you here is the autocorrelation for my 45 characteristics, either the monthly one, that's the orange line, or the annual autocorrelation. What you can see is that a lot of these characteristics are persistent, which means if I have access to prior realizations, I can use it to infer what a missing value could look like. There's also a lot of information in the contemporaneous cross-section. What I'm showing you here are pairwise correlation characteristics averaged over time and stocks. So there are 3 takeaways from this slide. Number one, you can see there are a lot of these clusters. That means if I observe one characteristic in this cluster, I can infer very well what the other characteristics could look like. Number two, I do not know a priori what all these dependencies are. They're very complex. So ideally, I have a good model that can learn from the data what all these dependencies are. Number three, there are a lot of dependencies. So I really want to take advantage of all observed values. In fact, if you have a plot like this, a very good model to capture these clusters are latent factor models. And that's what we are going to show in this paper. Now, let me come to the model. So our data set is a 3-dimensional tensor. So we have around 8,000 stocks, which are observed for 600 months for 45 characteristics. And my goal is to estimate a low-dimensional model for this 3-dimensional vector or 3-dimensional array. And what we are using first is a cross-sectional factor model. So let's pick a specific month. So I'm left over with a matrix, 8,000 stocks for 45 characteristics. And I want to capture this contemporaneous dependency, like small stocks are more likely to be value stocks. I will do this with a latent factor model. So under quite general assumptions, you can estimate a latent factor model with principal component analysis. The way how you do it is you construct what I will call a characteristics covariance matrix, and then you look at the largest eigenvalues and eigenvectors. That's not going to work when you have missing data, right? You can't construct this covariance matrix. So what we employ here is a method of the GA papers that I have with Roshan. So what we are going to do is we are essentially using only the observed values to calculate this characteristic covariance matrix. So let's say I have two stocks, I and J. I only look at the characteristics that these two stocks share to figure out how similar they are to calculate their characteristic covariance. Then I calculate this overall matrix. The eigenvectors, the largest eigenvalues, will be my characteristic factors. Then I run a regression of my characteristics on these characteristic factors to get my characteristic loadings. Now, there are 2 points I want to mention here. I only use observed data in this regression, and it's a very specific weighted regression. So a lot of magic is going to take place here. We can show that this type of regression is taking care of very general missing patterns. We have an asymptotic theory, so we show consistency, asymptotic normality, etc. in the paper with Rushan. And again, what I want to emphasize is this works under extremely general missing patterns, and that's very unique to this literature. Okay, so we have now the contemporaneous information, but we also want to account for the time series. That's quite easy. Let's just include prior observations in a regression where I include my characteristic factors. When I run this regression, I get a model that combines both information sets. I'm going to use again this magical regression that does this type of weighting and uses only observed values to estimate the coefficient of this regression. I'm going to call this a backward cross-sectional model because it uses backward information and cross-sectional information. Now, I could also, in principle, use future information. I will call it the backward-forward cross-sectional model. There are a number of special cases where you only use cross-sectional information or only the time series. And of course, special cases are the usual imputed methods like previous value or the cross-sectional median. Now, let me come now to the empirical results. So everything I'm going to show to you today will be out-of-sample results. And our metrics will be the root mean squared error and the normalized version of it, namely the R-squared. So the way how we are going to evaluate our models are as follows. We take all our data and we are going to mask part of the data. Then we are going to estimate our model, impute those values, and compare it with the true values. Now, we are going to use masking mechanisms that are very realistic. So I will use block masking, where I mask 10% of the data in blocks of 1 year, because empirically data is missing in blocks of 1 year. And we're also going to estimate a logistical regression model that explains missingness. It is a very accurate model. Then we use this logistic model for the masking. Of course, we also have missing completely at random and in sample results. For each model, I have a local and a global version. So the local model is just using the prior months to estimate everything. The global model is stacking everything together in one pooled regression. The point is, if you use future information, you have a look-ahead bias. And that matters for certain applications that we have in mind. So our local model is going to avoid any type of look-ahead bias. So here are the main results. I'm showing you the out-of-sample R-squares. This is for the block missing patterns, but the results are very similar for the logit masking. So the main takeaways are our models, the local backward cross-sectional model and the global backward forward cross-sectional model that use all information. They're extremely accurate. So we get R-squared that are relative to the median here that bring us a huge improvement. And I want to emphasize in the paper, we have a really extensive study of all kinds of variations of this here. So we show the evaluation for type of missingness, beginning, middle, end, for different types of masking, for extreme quantiles, based on the size of the company, industry, over time, etc. So the takeaway for you is it works really well out of sample. You get very accurate imputed values. Now, I also want to comment on what information is actually relevant. So here I show you for our backward cross-sectional model, how much weight we put on the cross-sectional information and on the time series part. And on the right, I have the more persistent characteristics. On the left, I have the more volatile characteristics. And as you might expect, for persistent characteristics, using prior value is more important. For volatile characteristic, you look more in the contemporaneous part. But the takeaway is a good model needs to take both dimensions into account. And we do this here. Now, let's come to the asset pricing part. So there are two things I want to focus on. One is a selection bias. Selection bias is if I estimate a model only on the subset of fully observed data versus using all stocks with imputation. How do the results look like? Number two is imputation bias. How much does it matter how I impute my missing values? So that will be median imputation versus our imputation. So I start with the selection bias part. Here, I have a very simple analysis. I look at the average returns of long-only portfolios that either include or exclude particular characteristics. So the black line is essentially evaluated market portfolio, just by all stocks that have a certain characteristic observed. And the orange line is a long-only portfolio where I only buy stocks that have not this characteristic observed. What we can see clearly is there's an effect in expected returns because characteristics are not missing at random, and that needs to be taken into account. So what I do next is I estimate an asset pricing model. Actually, I estimate the IPCA model of Brian. The way how we're going to do it is we take the first half of the data that's our in-sample data, the second half of the data is our out-of-sample data. I estimate these conditional latent factors. This gives me an implied SDF, and I will look at the Sharpe ratio in and out of sample for different numbers of IPCA factors. What you can see here is, and that is the orange part, here I estimate my pricing kernel using only the fully observed data. The blue one uses all data where we use this local backward cross-sectional method to impute them. You get uniformly higher Sharpe ratios. And you get substantially higher Sharpe ratios if you take all the data into account, sometimes up to a factor of 2 in improvement. So the takeaways in investments that use only a subset of fully observed stocks is number one, suboptimal, number two, not representative for the overall economy. Now let's talk about the imputation bias. So here I want to compare what happens if I use a median for imputation or our method. And we're looking at a very standard exercise. So we are using cross-sectional regressions. So I take returns, I regress them on my characteristics. This gives me characteristic factor mimicking portfolios. The mean of these portfolios is the risk premium that are associated with the characteristics. Now, if you use median or our method, you will get different results, but we want to make a statement about what is a better result. So what we're going to do is a masking analysis. So I take all my data, I'm going to run my cross-sectional regression on all the data, then I'm going to mask data using my logistic regression model that very closely mimics the empirical patterns of missingness. Then I'm going to impute data in different ways, run my cross-sectional regressions again, then I compare risk premium estimates, etc. Here, I show you the absolute error in risk premium estimates compared to the benchmark where I had access to all the data. The orange line is the median imputation, blue is our method. You get uniformly more accurate estimates for the risk premium with our method, and you get substantially errors for certain characteristics if you use median imputed values. Now, this result does not only hold for the mean, that means the risk premium estimate. If I look at the correlation of my characteristic factor mimicking portfolio with the benchmark, either for our imputed values, that's blue, or the median, that's orange, you see all moments are distorted when you do median imputation. So we have correlations up to 100% with the benchmark, and you have sometimes very low correlation if you do median imputation. Just to illustrate this, I'm showing you here the cumulative returns of these characteristic factor mimicking portfolios. And I'm showing this for representative examples. The paper has it for all the other examples. Here I've booked a market investment and sales over price ratios. Blue is the benchmark. Orange is our imputed values. We are very close to the benchmark. If you use median imputations, you get a completely distorted time series. That means not only the risk premium is wrong, your standard deviations are wrong, your correlations are wrong, you get wrong inference. One thing I want to emphasize, even if a characteristic does not have any missing values, that would be size. So our logistic regression model is not going to mask size. But if you run a regression on all characteristics and you impute some values wrong, it can even affect your estimates for those characteristics that are fully observed. So you get wrong inference on the risk premium for size. Now the paper has many more results. So we show results for the selection bias for univariate sorts, for univariate factors, etc. All what I've shown you here will carry over to these different analysis parts as well. So let me wrap up here. So this paper is a systematic study about the missingness in characteristics. We show it's a pervasive problem and simple solutions don't work. We provide a new method to impute missing values. It's a parsimonious, quite simple model, easy to use, combines time series and cross-sectional information, and it works really well. And it works theoretically. We can show it under very general missing patterns. Just as a final comment, missing data will become more and more important in our age of big data. And there are a lot of interesting new data sets, for example, ESG data, international data, tax data, where missing data is a huge problem. So it matters to be aware of this problem and to think about solutions to this. We think of our paper as the first step into this direction. And I look forward now to Sergei's comments. Thanks.
Okay, thank you. So our discussant will be Sergei Kozak from University of Maryland.